Hi, and welcome back to another week of supervised learning. This week we're going to be learning about generalized linear models, but to set up for that we're going to first take a look, in this video, at the important class of probability distributions known as the exponential family. In previous weeks we've introduced simple and multiple linear regression as ways of modelling real-valued outcomes based on one or more predictors. We've also extended this idea to deal with classification problems by developing logistic regression for binary and multinomial regression for categorical outcomes. In this video, we'll introduce the exponential family of distributions, and we'll use this family of probability distributions in the next video to extend our linear model to accommodate outcomes with a wide range of distributions within a single unified framework. This video is going to lay down the foundations for that, and be warned it does introduce a lot of new terms and definitions which we can add to our data science dictionaries. If you need to come back to those definitions later in the week or later in the course, then that's perfectly normal. So, what exactly is a probability distribution within the exponential family, and what does it look like? For a random variable y with a single parameter theta, to belong to the exponential family it must have a density function f of the following form, where the functions eta, t, a and c are all known, and the values that y can take doesn't depend on the parameter value theta. Let's examine this expression a bit more closely, and notice that the log density is going to be a function of the parameters eta times a function of the data t, subtract a function of just the parameters a, add a function of just the data c. In the final two terms, we can separate the data and the parameters, but in the initial term, we can't. In particular, notice here that the product here is a dot product, so while our functions eta and t will usually be scalar valued, they could equally take vector values and give a valid expression here. Most of the probability distributions that are commonly used when modelling data are going to belong to this family of distributions. For example, the Poisson, the exponential, and the binomial distributions all belong to this family, where for the binomial we additionally require that we know the number of trials n. We can also introduce some additional terminology here. So the distribution f is said to be parameterized in canonical form if the function eta is the identity function, so that eta of theta is simply theta. If, in addition to this, the function t is the identity, so that t of y is y, then the distribution is said to belong to the natural exponential family. I just claimed that the Poisson distribution is a member of the exponential family, so let's put that claim to the test. If y follows a Poisson distribution with parameter lambda, then the support of y is going to be the values 0, 1, 2, and so on through the integers, for any value of lambda. And the density function for y is going to be given by lambda to the y, e to the minus lambda, all divided by y factorial. Therefore, our log density function takes the following form, and we can identify our terms within this. So the Poisson distribution is going to be within the exponential family, where our function eta is given by log lambda, t of y is simply given by y itself, a of lambda is lambda, and c of y is minus log y factorial. This parameterization isn't currently in canonical form, but we could achieve this through the reparameterization of letting mu equal to log lambda. Using that parameterization, the Poisson would have both eta and t as the identity function, and therefore belong to the natural exponential family. Okay, so suppose now that our probability model has more than one parameter, that has m greater than or equal to 1 parameters, to consider this in generality. And we're going to store those in a parameter vector that we'll call theta, where each element of theta is an individual model parameter. In this case, y is going to belong to the multi-parameter exponential family if its probability density can be written in the following form, where the functions eta I, ti, ai, and ci are all known for I from 1 to m. And again, we require that the support of y doesn't depend on the parameters theta. We can express this in one of two ways. We can either specify the functions a and c per parameter, having these indexed by I here, or we can combine them into two single functions over all of the parameters. Just as in the single parameter exponential family, many of those distributions used most commonly in applied statistical modelling come from this family. This family includes distributions like the beta, the gamma, and the normal distributions. So let's make this multi-parameter case more tangible by considering another example, the normal distribution. We should notice here that we're considering the case where both mu and sigma squared are unknown, so that if y follows a normal distribution with mean mu and variance sigma squared, it has the following probability density function. Taking the logs of both sides, we find the following expression for the log density. And notice here that the first two terms involve both the data and the parameters, while the third and fourth are only in the parameters. Adding a somewhat artificial final term here of 0, we can see that that term depends on the data only. Therefore, we've shown that the normal distribution is within the multi-parameter exponential family. We can also show that it's in the natural exponential family, with natural parameters eta1 and eta2, by taking eta1 equal to mu over sigma squared, and taking eta2 equal to minus 1 over 2 times sigma squared. This leaves us with our sufficient statistics, t1 and t2, being equal to y and y squared respectively, a being the remaining non-zero terms here, and c being 0. Now that we've introduced the exponential family of distributions and met some examples with a single parameter or multiple parameters, let's investigate this family of distributions a little bit further. Here we're going to let f of y be the density function of a random variable that belongs to the exponential family. Because this is a density function, we know that it must integrate to 1, and if we substitute in our expression for the exponential family density, and then differentiate both sides with respect to the parameter vector theta twice, then we can show the following results. That the expectation of our summary statistic t is given by the gradient of the function a, and the variance of our summary statistic t is given by the Hessian of the function a. To really understand the usefulness of this result, let's focus on the case of the natural exponential family, when there's only a single parameter. In that case, our expressions are going to simplify greatly, and we see that the first derivative of the function a gives us the mean of our outcome, and the second derivative gives us its variance. This relationship is a very nice one, but can be overly rigid sometimes in real modelling scenarios. We can change the dispersion of our outcomes without changing their mean by introducing an additional model parameter, which we're going to call phi. So going into a little bit more detail on this, single parameter models in the exponential family can only match one moment of the sample, and that's usually going to be the first moment, the sample mean. A fixed relationship is then assumed between the mean and the variance of our outcomes. For example, the Poisson distribution has these being equal, while for the exponential distribution, the variance is the square of the expectation. This is in contrast to multi-parameter models, such as the normal distribution, where the parameter values can be selected to adjust the dispersion of the responses without altering the level of the responses. We can extend the single parameter models in the exponential family to allow them to have this type of adjustment, and we do so by adding an additional dispersion parameter, phi, to the distribution. This is going to result in a probability density function of the following form, where our first terms are divided by phi, and our constant term at the end, c, is now a function of both the data and the dispersion parameter. For the natural exponential family models, this is going to be known as the exponential dispersion model, and we have some really nice relationships going on here. The expectation of our response is the first derivative of our function a, and the variance of our responses is going to be our dispersion parameter times the second derivative of a. These relationships can be used to demonstrate several pleasing properties of the exponential dispersion model, which forms the basis of generalized linear models when our dispersion parameter is equal to 1, and the basis for quasi-GLMs when the dispersion parameter is estimated along with the model parameters. So just going to take a minute to talk through the nice properties that fall out from this exponential dispersion model. This seems like a lot of information, but we'll just take it slowly and go through one step at a time. Since the expectation of y is given by the first derivative of a, the mean of the response depends only on the main model parameters, that is theta. The variance of the response is given by phi times the second derivative of a, and so depends on both the model parameters theta and the dispersion parameter phi. Since we know that the variance of y is going to be positive for any interesting model, we know that the second derivative of a is either always going to be positive or always going to be negative. This tells us that the gradient of a is either strictly increasing or strictly decreasing, and it's therefore an invertible function. What this allows us to do is invert the relationship mu equals a prime of theta, meaning that we can always write the model parameter as some function of the expected outcome. We can write theta equals h of mu, where here h is going to be a prime inverse, which is called the link function. And this link function is going to be important in the development of GLMs later on. Then we can use this invertible relationship to write the variance of y as phi times the second derivative of a, or equivalently, phi times some variance function of mu. We therefore have that if we know either theta and phi, or mu and phi, then we're going to know both the mean and the variance of our outcomes. So we've covered a lot of ground and introduced many new ideas in this video. For a start, we've met the exponential family of distributions and shown that the Poisson and normal distributions belong to the exponential family, and in particular to the natural exponential family. We've defined what it means for an exponential family model to be parameterized in canonical form, and what it means to be part of the natural exponential family. Finally, we've extended the single parameter exponential family of models to allow both under or over dispersion, hence creating the exponential dispersion model. In the next video, we'll go on to develop GLMs as a unified regression framework for responses that have any distribution in the exponential family. Thank you very much for your time, and I look forward to seeing you in the next video.